All right, so this lesson is on solving systems of equations using graphing. So let me just first say that solving systems by graphing is probably the hardest way to solve a system because it requires you creating a graph, graphing the equations, and finding where they cross. So there are other ways using substitution or elimination. Most people prefer substitution, but it really depends on the equations that you're giving what the best method is. But this method, solving by graphing, always works, okay? But it's probably the least used method. So first of all, what is a system of equations? So a system of equations or linear equations is just two or more linear equations. So if you have two or more linear equations that go together, we call that a system of linear equations. So when we talk about solving them, what do we mean by that? So any ordered pair, and so what we're talking about is an XY ordered pair that makes all of the equations in the system true is a solution of that system. So any XY ordered pair that when you plug it into the equation makes that equation true, and it does that for all of the equations, we call that the solution of the system. All right, so I'm sorry, excuse me. When you graph them, if the lines cross, that point where they cross or where they intersect is where the solution is. So this is the XY ordered pair that is a solution to each of these lines, or in other words, each of these equations. Now, if you have two lines that are the same, so let's say you have two equations that really are the same thing, just written in different forms, and you graph them and you get the same line, then that means there's infinitely many solutions, because every XY ordered pair that's on here will be a solution to each of the equations. Now, if the lines don't cross at all, in other words, if they are parallel, then that means there is no solution to that system of equations. They have no XY ordered pairs in common. Just a little bit of verbiage here. If there's one solution, we say that the equations are consistent and independent. If there's infinitely many solutions, we say the equations are consistent and dependent. And if the lines don't cross at all, if they're parallel, then we say the equations are inconsistent. All right? So to solve a system by graphing, all you can do is graph these two equations and see, number one, if they cross, and if so, where do they cross? All right, so if we look at this first equation, this is in slope-intercept form, y equals mx plus b. So the slope of this one is 1. So the slope is 1. I'm going to write it as 1 over 1 for rise over run. And the y-intercept is 2. So if I was to graph this first equation, I would first graph the y-intercept at 2. And then for the slope, I would rise 1, run 1. This is a positive slope, so I know it's going to lean to the right. So I'm going to go up 1 and to the right 1. And so I'll just put a few points there and draw a line through those. Extend this out a little bit. Something like that. Put arrows, meaning this line continues on indefinitely. So that's the first one. The second one, I'll do in a different color. The slope of this one is 3. I'm going to write it as 3 over 1 for rise over run. And the y-intercept is negative 2. So it crosses the y-axis at negative 2. The slope is again positive, 3 over 1. So I'm going to rise 3, 1, 2, 3. And I'm going to run 1 to the right because, again, it's a positive slope. If it was a negative slope, I would have gone to the left. So 1, 2, 3, 1. Which, by the way, there you can see that's the point where they cross. So let's go ahead and draw this line here. The line is really not necessary. My arrows here. And so right here is an XY ordered pair that is a solution to both of these equations. So this ordered pair is 2, 4. And so 2, 4 is a solution to the system of equations. So if I plug in 2 for, so this is an XY ordered pair, if I plug in 2 for X into both of these equations, you will get 4 out for Y. So I'm not going to write it down, but just follow along. So if I plug in 2 to the first one, 1 times 2, so it's just 2. 2 plus 2 is 4, right? And this one I'd have 3 times 2 is 6, minus 2 is 4. So 2, 4 is a solution to both of these equations. All right, so remember there's either one solution, there's no solutions if they're parallel, or there's an infinite number of solutions if they are the same line. All right, so let's look at another one. This first one, rewrite it over here. It is, excuse me, it is in standard form. Standard form is ax plus by equals c. So 2y minus x equals 2. And so remember, you can graph equations in standard form. Hold on. I'm going to get my little box here. Bear with me here. I'll pause this so you don't have to watch me create this box. I'll be right back. Let me make a box. All right, so I'm back with my box. So you can graph these by finding the x and the y-intercepts. So the y-intercept occurs where x is 0. So if I just cover up the x, make it 0, I have 2y equals 2. 2y equals 2. Divide both sides by 2. And so the y-intercept is at 1. So it crosses the y-axis at 1, right there. Now let's cover up the y value because the x-intercept occurs where y is 0. So now be careful. This minus sign belongs with this x. This really is negative 1x equals 2. Divide both sides by negative 1. And x equals negative 2. So it crosses the x-axis at negative 2. So that's right there. And let me draw my line through there. Click the wrong thing. No, I want this. So, let's see, 1 over 2. Hopefully that's enough. My line jumped on me. Sorry, I'm gonna get it perfect. Let me extend this out. Put my arrows on the end. All right, so that's the first one. The other equation is in slope-intercept form. Y equals mx plus b. So the slope is 1/2. It's a positive slope, it's leading to the right. And the y-intercept is 1. So it crosses the y-axis at 1. Okay, well that's really nice. There's my solution right there. And the slope is 1/2. So I rise 1, I run 2. Okay, well, guess what? They end up being the exact same line. So what is the solution to this? The solution is that there are infinite solutions. That's not how you spell infinite. I-N-F-I-N-I-T-E. Infinite solutions. Because the lines are the same lines. So remember, there's either one solution if they cross, infinite solutions if they're the same, and then if they're parallel and they don't cross, then there's no solutions. So guess what the next example is? All right, so if you remember, the property of parallel lines is that they have the same slope So this is in intercept form. So they have the same slope, but different y-intercepts. So the y-intercept of each of these, that one's 2, this one's -1. So this one crosses at 2, this one crosses at -1, and they both have the same slope. The slope is 2/1. So I'm going to rise 2, run 1 to the right. Rise 2, run 1 to the right. And so you'll see that these lines are parallel. Rise 2, run 1, like so. Let me do another one here. Rise 2, run 1. Okay, so since the lines are parallel, that means there are no solutions. All right, so that's solving by graphing. I got one more thing for you. I got a word problem here. All right. It says scientists studied the weights of 2 alligators over a period of 12 months. The initial weight and growth rate of each alligator are shown below. After how many months did the alligators weigh the same amount? All right, so they're looking for when they have the same weight. All right, so you're looking for a solution to both of these that works for both of them. So alligator 1, its initial weight's 4 pounds. Its rate of growth is 1.5 pounds per month. So we have 2 variables here. I'm going to use W for weight, and I'm going to use T for time. And the time is in months. That's our 2 variables. All right, so for alligator 1, let's look at alligator number 1. His weight, or hers, is 4 pounds plus, so we just put 4 is 4 plus 1.5 times the number of months. All right, alligator 2, its weight is 6 pounds plus 1 T, and I'm just going to write T, and I don't need to put the 1 there. So this form, while you don't see X and Y, this is slope-intercept form. All right, so this coefficient of T is the slope, and the 4 is the Y-intercept. So I'm going to write this 1.5T as an improper fraction, just because it's going to make it easier for me to graph this. So the weight is 4 plus 3 halves T. So let's go ahead and graph that. So first of all, my axes here says X there, but this is going to be T, and this is going to be W. T is the independent variable, and W is the dependent variable. W, the weight, is dependent upon the number of months. So alligator number 1, its y-intercept is 4, and its slope is 3 halves. So up 3/2. 1, 2, 3/2. It's a positive slope. 1, 2, 3/2. All right, and I'm going to draw a line through there. And actually, the truth is, let me fix this. The alligator started at 4 pounds, right? So it really doesn't continue in this direction. It's just the weight is just going to keep increasing over time. So I shouldn't have extended that out, right? Because over here, if this is time, you can't have negative months. So time starts at 0. So really, you're only interested in quadrant 1 here, where you have positive weight and positive time. All right, the next one, alligator, it crosses the W axis at 6. So that's right there. And its slope is 1 over 1. So up 1 over 1, 1 over 1, up 1 over 1, up 1 over 1, and guess what? They cross right there. So let me go ahead and make this line. So this is where they cross, which is a weight of 10 pounds. So they both weigh 10 pounds. That's a S, I swear, promise. And the time is at 4 months. Now, let's go back and let's see what the question was. The question was, after how many months did the alligators weigh the same amount? And so the answer is 4 months. At 4 months, they both weighed 10 pounds. All right, so that's solving systems by graphing. So hopefully that was helpful and useful to you. If so, give it a like and a subscribe. Until next time.